record this one. Cool. So, before we go into the details of homework 2, P2, let's just talk about your reflections for your homework 1, P2. So, let's take 1 minute of like reflection to see what was the challenges that you guys figured out for homework 1, P2, what strategies and resources helped you the most, and what would you do differently if you could just start over. So just think about it by yourself. If you want, you can talk with your other people for like a couple of minutes, and then I'll just ask you guys how you felt about homework 1, P2. Cool. So yeah, you guys can discuss if you want about it. So yeah, all right. So guys, so guys, can you guys hear me? All right. So can you guys tell me what was the challenging things that you guys figured out for homework 1, P2? Yeah.
I think first thing is getting our DM to start. That took a lot of time for every single one of us.
Yeah.
Spending close to 1 hour sitting and trying it over and over again. That was one thing. That was one challenge. I think I think that was one challenge. I think.
Any other more challenges that you have had? So like, did you focus on only GCP or did you guys try GCP, AWS, or GCP? All right.
I think also it's a significant portion of our credits. I think we lost, each one of us has lost around 100, 120 credits already.
On just setting it up? Or just setting it up?
Setting up, like the overall training that the
I see. Okay. And did you just focus on doing like trying to SSH into the instance and try running it, or did you guys try focusing on it?
On collab.
So on Collab. And I think this is also like issues from previous semesters as well. That especially when people are working on Collab with GCP, there are not many instances that are there. So it's like it's more of a trial and error in that case. But you would be getting a lot of instances when you try doing the SSH way with VS Code. So that's one way of doing it. Plus, the way of doing it with VS Code also helps you to basically automate your run. So you can basically use tmux and basically just load your laptop once it's training. So that's why I prefer everyone to just try using VS Code rather than Colab. Because with Colab, you cannot just shut down your laptop and open it, and it's probably not going to be like showing you the results of your training at that point.
Doesn't
So,
won't be help.
yeah, Wondy helps you in that case. But usually if you do it with Colab, it just stops and it's like
Yeah.
truncated output. So yeah, that's one issue that I have seen as well. So my recommendation for that would be to just try doing VS Code SSH and use tmux for just automating your runs. Any other challenges you guys faced from homework 1 P2? Or was it like a very easy homework? Okay. So let's move on to the second question, which is basically what strategies or resources helped you the most? Anyone like, what do you think was very helpful? Was the recitations helpful? Was like recitation 0 helpful in that case? Or like anything of that kind?
We attended an officer, we tried to get in touch with our PMS, and I think that meeting also helped us push, reach the high cutoff from our native cutoff.
All right, that's great. Okay. And the third question would be, what would you do differently if you could start over? So can I ask the question from this side? Like, if you guys were able to start over your homework 1 P2, what would you guys do differently? I would randomly start picking people if I don't get a response. 3, 2, 1. Okay, the guy with the maroon shirt.
But we do information kind of assume we pick smaller models to try, for example, Adam W on it. That ended up being very indicative of how it performs on bigger networks.
I see.
So I think we probably would start with like a bigger or like funnelize the overall like architecture way sooner and then do it later.
I see. So you guys basically start with the smaller models and try figuring out your applications with that, and then once you fixed on your parameters, you went on a bigger model.
Yeah, and then once it's a bigger model, we found out we had to retry.
Correct. Okay, that's a common issue as well. So usually what I say to people is to just fix up your models, reduce the number of data points in your data set, train it on smaller epochs, get your hyperparameters tuned with that, and then go for a long run. But that is something which you guys can start doing from homework 2 P2 onwards. So homework 1 P2 was essentially just for you guys to get a small flavor on how the rest of the homeworks are going to be. And the first main difficult homework is going to be your homework 2 P2. So just bear in mind with that, and we'll see how it goes. But any others, any other things that you guys would have done differently if you were able to start over?
I think we did waste some time after the low cutoff. But I think running through more station might have helped.
I see.
Yeah, like before we fix our.
All right. And what do you like study groups helpful when you discuss all your hyperparameters and all that stuff?
I think we did a lot of work as a group, so that helped. So we shared what worked, what didn't work, and that saved each other's time as well.
Perfect. So that's the whole point of study group, so that you guys can at least share like what results you guys got with your different hyperparameters. We don't want you to share code, but we want you to share the knowledge that you gained by doing different studies. So you can't do updations by yourself, and that's why you need a group to basically spread out results. And that was the point of the study group.
I have some questions.
Sure.
So let's say one of our teammates has trained a model with certain hyperparameters. Can we not get these waves when train further or try to do things? Because I mean, it's just we know what they're doing, we have their ability, and training with the same ability from scratch is just going to waste a lot of resources.
I see. But the thing is that that will come into the gray area of academic violation, which we don't want anyone for it to come in. So it's like we wanted to do updations differently, and it's like the moment a guy gets, let's say, 87% accuracy, he just tells you what hyperparameters he's used. He'll tell you like whatever architecture he used, and you basically do the coding by yourself, and you get to that point. Because most of the time, even in study groups, there might be just this one guy who gets you the best results, and if he shares literally all the code of yours to basically to the entire group, then the other three people are not learning essentially anything. We want everyone to learn equally, but at the same time, we want everyone to run different ablations so they can find the best course for getting the best marks essentially.
Yeah, we get that, but
I agree with that. Like it makes sense. Like that gray area was something we also talked about, and what he said makes sense. It's just that once, like we went through a lot of operations, we came up with a fine set of parameters. The issue is we then have to individually do the same training 4 times, just wasting a lot of resources because they're doing the same thing for multiple things.
Yeah,
So that's the only like concern or thing we wanted to bring up. Like, is it possible to share those data?
yeah, the thing is that that's not basically allowed, because like at the end of the day, then it's like you guys will be just copying one guy's code and not actually training by yourself. So we want everyone to train, we want everyone to basically learn how to train a model. So if one guy trains, like let's say, and he gets 87% accuracy, and we just take his PTA file, run it for one epoch, and then just use the reference EFP file and submit it, that you're not training anything in the end of the day. You're just basically trying to you're basically just fine tuning that one model for one information and trying to get a bit. So we don't want that to be like your training thing. We want you guys to know how to train anything from scratch. But yeah, good points. Anything else that you guys wanted to talk about? What you could do if you could like basically start over? No? Okay, let's move on to the next slides. So yeah, great job on figuring out what all you guys have done. Homework 1P2 and homework 1P1, I hope it wasn't extremely hard. Now we're coming on to the homework 2 side, which it's not actually very, very hard per se, but it's going to be a little bit more time consuming compared to your previous homeworks. So with that in mind, we'll just give you a small brief push for you guys to how to start homework 2P2, and after homework 2P2 we'll also show you on how to do it for homework 2P1, and hopefully that will at least let you help you navigate through the homework. So we're not going to go into the theory bits of what is CNN, what is that, and all that stuff. We're just going to be giving you like a small brief introduction of things, and we'll tell you like how the coding works of it in general, and from there we'll push forward. So yeah, let the war begin. First thing, Kaggle shoutouts to the top 10 submissions. You guys did a great job on whoever the top 10 were. Yeah, you are awesome, and basically you know it, and even the entire people who are taking IDL also knows it, and the TAs also know it. So great job, guys. Another Kaggle shoutout is for the funny names that we found out in Kaggle. Life needs a warm restart. I feel so as well. Collab eats my lunch money. Yes, for sure. Chef Tate, I hope you were cooking something good. And 86 before GTA 6. I would like to know what you mean by that, but okay. So we need more of this. We are happy if you guys can like just have some fun when you guys do the homework. So more funnier names, more better. A little bit more work for TA as well. It's totally fine. So let's start with the overview of homework 2P2. So like I said, homework 2P2 is going to take a lot more time than homework 1P2. Models will be harder to develop, train, and converge. And the most important bit is models must be written by yourself and should be trained from scratch. So this homework is going to be a little bit different from your 1P2 because there are like a lot of different pre-trained models that exist already. But we don't want you to just basically just grab it and use it and train it. We want you to like learn how to do it, learn how to code that thing. So that's going to be the main surface for homework 2P2. And also, you would want to use what you have learned from homework 1P2. And for this homework, especially, please start early because it is going to take a lot of time to train. So yeah, but feel free to take a day's break, enjoy yourself, relax, do some yogas, whatever you guys want to. And then, yeah, drink something and then just come and start your homework 2P2. Hopefully you can start it by this Monday and then it should be Gucci. So I think there are questions on chat. Cool. All right. All right, so let's go to the thing. So the goal of the homework bootcamp. So it's basically to just get you head start, to help you get started with homework 2P2. And the agenda for today is we'll be talking about the problem statement for homework 2P2, and then we'll be discussing the workflow of the homework. Basically, there is data loading and pre-processing, building a model, training, monitoring, testing, and Kaggle submissions, and different loss functions for your task. Hopefully, most of these, like the data loading and pre-processing bit, we have already coded up for you. We don't want you to waste time on that. But you guys will be focusing more on the model building side and also trying out different loss functions. So these two are like really, really important for your homework, Torpedo. And we'll be diving a bit deep inside this. But at the same time, we know that we haven't gone through the CNN lectures yet. So we'll not try to basically give you the theory information because then everything will just go over your head and I'll probably lose the entire crowd at that point. So after that, we'll just have a small FAQ and then we are pretty much done with homework 2P2. So the problem statement. You'll basically be doing two tasks with just one model, but there's only one casual submission. And the two tasks in hand is face verification and face classification. Okay. Sounds simple enough. So first thing is face classification. Does anyone want to tell me what is face classification? Like just by the word face classification.
With that,
Yeah. So
what you're can be a boy or girl.
So it can be like I have different faces of people. I'm trying to classify whether they're a boy or girl, or it could be that I know who this face relates to what name, and then I'm okay. If this picture comes in, okay, I know this guy is X person, Y person, Z person. That is essentially just classification, right? So if you see the image over here, it's like I give an image of this guy, it tells, okay, he's Satya. If I give a picture of Mark Zuckerberg, it tells me, okay, it's Mark Zuckerberg. And if the guy is not even there, let's say if Elon Musk wasn't there in my data set, which is going to be pretty sad, it would be like, I haven't seen it before. Like there should be a class, there should be a class for that as well. So basically face classification is you just trying to identify the identity of the person based on the image. Okay. Face verification, on the other hand, is a little bit different. I'll be giving you a pair of images and I'll be asking you, okay, whether these two person are the same. So let's say if I give you an image of myself and I give you an image of Mark Zuckerberg, and I'm like, okay, is the image of me and image of Zuckerberg the same person or not? So that is face verification. And face verification is mainly used on most of your like security things, for example, your smartphones, or let's say if you have to open a door with your face, that's also where face verification works. Classification, on the other hand, you just basically use the classification model to do your face verification. But yeah, these two are like different tasks, but they generally involve using the same model. So workflow. So now we'll talk about how the coding bits are in your starter notebook. So homework part two's ideal workflow would just basically be downloading your notebook, complete all the to-dos, and just ensure your code runs and reaches a very low cutoff. So reaching the very low cutoff for homework 2P2 shouldn't be that tough. We have defined you the model, what you have to use. You might need to do a few ablations. Most of the coding is done for you. You can just introduce normal cross entropy loss, and then it should be good to go. But the next important step after getting your very low cutoff is to divide your experiments among your different group members to achieve the high cutoff. And the high cutoff, we usually will tell you like maybe a 1 week before the deadline. So try getting the best possible accuracy you can by then. So let's talk about the components in your part two. The first thing is data loading and pre-processing. The second would be building up your model. The third part would be just training and monitoring what it is. Fourth one is just Kaggle submission. And fifth one is trying different loss functions and fine-tuning that model. So let's go into data loading and pre-processing. We are just using something called image folder from the Torch Vision library, which basically means that we have one big folder with different subfolders, and those subfolders essentially tell you what is the identity number for the person. And we just use that. It's just one line of code to basically get your dataset class done and data loader essentially. So the image folder class will just automatically infer the labels and make the dataset object, which we can just pass on to the data loader. So it's just a one line of code that we use for this. And we also basically write our own dataset class, which returns a pair of images for verification. So we have basically a TXT file for your validation and test set for your, what do you say, for your verification task, and you basically just need to call that out and see whether the two identities match or not, essentially. So the dataset and data loader class, you guys don't need to change anything in that area because everything is coded up from our end. The only thing that you'll probably need to do is basically do different transformations to your images, which we'll be talking more in greater details as I'm going with this bootcamp. Yeah, so let's talk about the different augmentations on your images. So first of all, why do we need to use image augmentations? Anyone, if anyone's done a CV class or DL class or ML class before?
Generate more images of the same images, so you change the direction, you either flip it or so that you get a larger data set.
Okay, generalization, that's good. Anything else?
And different conditions, so like say every image cannot be the same, so adding abilities to correct the color of image and all that stuff helps to better understand.
Great. Good. Anything else? Oh, cool. No worries. So, the first thing is like what you mentioned. It's basically to emulate more data. You're not necessarily increasing the number of data points in your training, but what you're doing is you're just trying to apply different augmentation techniques on your different epochs. And that basically emulates more data and helps you to generalize or improve your training performance. The next thing is to prevent overfitting. You don't want to overfit to a particular area. Let's say like if I have trained images of just a person standing like this for like all my classes, but my test image has a guy just slanting his head up a bit. I want my model to generalize to that thing as well, right? So I would try to apply different data augmentation techniques for that. The third thing is basically invariance. Training the model on transformed images teaches you to recognize objects independently of the orientation. So basically, if my image was a little bit tilted in my test set or in my, let's say, validation set, it should be able to generalize to it. That's basically what it means. And the fourth one is just basically telling the same thing of the third. So here are some sample augmentations. So this is first thing is random crop. I'll ask you, do you think this is a good augmentation technique? So
For face verification, it might not be the best technique because it might crop the face.
we don't want that to happen, right? But it could also be a good augmentation technique if it was able to capture the clips every single time. But that's not going to always happen, right? So in these type of augmentation cases, it's really like dependent upon what type of probability value you use for it. Generally, it may not work as your face image might be like a smaller subset of what the actual entire image is. So we don't usually recommend to use random crop in that. But yeah, the next thing is random rotation. Do you think random rotation would be a good augmentation technique? Say from here, anyone? Do you think random rotation would be a good augmentation technique? Okay.
Yes.
So I would say random rotation would be a good technique if you're trying to keep your angles very low. Because at the end of the day, if a person is standing straight or a little bit slanted, that is something which is at the norm. But you're not going to see images of people doing a handstand, right? And be like, okay, can I take my image of this and I want to put it into my machine to try to train a model. So I would say if you're using random rotation in that case, try to ensure that the angle that you're using is a little bit less, let's say between 20 to 30%. Don't use anything above 90 and just completely invert your image. So horizontal flip, it's a good transformation because it kind of replicates what can happen in real life scenarios as well. On the other hand, if you see vertical flip, not so great. You're not going to be finding people doing handstands and putting that inside your data set. Color jitter, that's another type of augmentation technique. It is pretty good because you're able to capture different type of let's say colors that can occur, and you don't want to basically generalize to a particular, let's say if I have orange in my data set for like so many times, I don't want to say that, okay, orange is essentially a human being, right? So for that, we use color jitter. Then there is like different augmentation techniques which you guys can try out. That's a random perspective. that may or may not help. Then there is also things like cut mix and mix up. I would highly recommend you guys to look into that as well. We haven't gone great depth into that. But yeah, try out cut mix and mix up as well for this homework. So some of the transformation tips, consider trying to normalize your data. You can use torch vision.transform.normalize. We also put up a link in the homework 2P2's Piazza post on how to normalize your different images data. So you guys can use the same thing and follow and try to get the values and try to normalize your data in all three different channels. So common issue is basically type error. Input tensor must should be a torch tensor. Just make sure that you check the sequences of your transformations because let's say, for example, cut mix or mix up, they usually don't happen in the start, they usually happen in the end. And there are different augmentation techniques that usually figure with that same thing. So if you guys get any of this sort of error, just make sure that it's probably going to be because of how you guys tried doing the transformation techniques. So this is what a typical transformation pipeline would look like. You just do a transform.compose, and inside that you basically add all your augmentation techniques. And after adding your augmentation techniques, you want to convert that image to a tensor so that you can put inside your model. So you basically do transforms.to tensor. And after converting it to a tensor, only then you normalize your basically image. And if you see over here, this is the mean and the standard deviation values for your three channels, which you'll have to give. You can basically calculate that with the link that we provided in homework 2P2's Piazza post. And that's pretty good. If you guys want to look into different transformation techniques, just go to this link over here. It'll take you to the the Torch Vision official area where they tell you the different transformation techniques that you can apply. Play around with it because that's going to be like your high cutoff is going to be like very dependent on this. Okay, so if your final images after transformation looks like this, it means you have done a pretty good job. Your model may generalize good, may not, but at least this is what is expected. But if it looks something like this, then we might have a problem and you might need to change your augmentation techniques. But yeah, let's come into building the model. So over here, what's up?
Just had a question on augmentation. So is it fine if we use some standardized library like augmentations for doing the augmentation?
Yeah, you can use whatever you want. You can also use Torch Vision library. You can use a Torch Vision V2 library. So there are like different libraries for your augmentation technique. We completely recommend you to use it. You don't need to code anything scratch from it for augmentations. That's going to be like some next level work we can put in.
Are we expected to have image processing techniques like grayscale there?
Yeah, grayscale, everything you can try out different things. Yeah, go ahead. Just do whatever you want now. But you should have this intuition of whether it will work or not. So you can train it for like 5-6 epochs, see if it works or not. If it doesn't work, just remove it, try.
Is there a problem where actually look for the data around the same class and then
You can try in that, but if it performs well or not, I cannot guarantee it because previous semesters people have tried doing it, but it did not actually give them results. So that's why when we build up this homework, we selectively choose the important images. And based on that, we basically get you your classification cluster so that basically the verification has components from your classification. So, yeah. Anything else? Okay, let's move on to building a model. So, first thing, I think I made it clear. We are not going to be using linear layers in this case. We are going to be using something called convolutional neural network (CNNs). But do you guys know why are we using CNNs and not linear layers? Anyone? Why do you think we're using CNNs and not linear layers? I mean, I know that Rob hasn't got it yet. He's going to probably teach you next week.
the position of the particular pixel matter and we do that.
Yes, one of the main things is the spatial features. Linear layers don't capture it. Any other things that you guys think it's important?
Using linear layers would be very inefficient, because in CNN, right?
Yeah.
So the parameters are shared across the entire image. So there is a convolution kernel that convolves rather than having different weights linked to each input pixel.
Okay. Yeah. Brilliant answer. That's also what I was expecting. So yeah, another thing, a good thing about trainings is that they are shared parameter learning. So you guys have kernels where you basically convolve to the image and basically use that. And I think like this semester people are going to do a great job in this homework because I'm getting brilliant answers. So there is one more important thing that I want to talk about. Let's say if I had an image of let's say 1,000 by 1,000, and I have like basically 1 million hidden neurons. Do you know how many parameters will be, how many learnable parameters will be there in this case? There would be 10 raised to the power of 12 trainable parameters. That's like a very huge model. I don't think even LLMs are that big. So if we actually use linear layers, that's the big issue, which he mentioned. Brilliant answer. Other thing was we also lose spatial features in that. So because of that, we want to use something else. So what are we using? Our hero over here, CNNs. Yeah, but why CNNs? They're good in capturing your spatial patterns. They handle your 2D images very well. They're good for feature detections. That's basically using your kernels and looping through your entire image and getting the best optimal weights for it. They share parameters across the local regions, reducing the number of parameters and basically translational invariance. Do you guys know what do I mean by translational invariance over here? Anyone? Okay. So translational invariance over here basically means that if I have an image of, let's say, the image of the person is on the right side, and there's another image of the person on the left side, I want basically the kernel, or in this case, whatever you're using, to basically capture the same face, if it's there either on the right side of the image or in the left side of the image. So that's basically saying that CNNs are good in capturing whether it's on right or left or bottom, top, anywhere. So that basically means they're translational invariants. Linear layers, on the other hand, they are not translational invariant. So, but in this homework, CNNs are not going to be enough. So you guys will need to do something else. And for that, you need to use basically different complex architectures which help you to converge your model and mitigate different overfitting. So some of the good models that we recommend for this homework is ResNet and SE ResNet, and there might be some magical architecture we might not have tried out. You guys can go ahead. But yeah, try focusing on ResNets and SE ResNets. We have all our TAs trained up for that. Magical architecture cannot guarantee. There might be something out there that might get you like 98% accuracy or something. I don't know. So let's talk about ResNets. I don't want to go in depth on what is a ResNet and like how it works and all that stuff. If I do that, then I think I would lose the entire crowd, and I don't want that to happen. So the main thing idea right now I wanted to teach with you guys is to convert the paper to a code. And for that, you need to understand what are the different blocks that they introduce in the code and how do you code them out. Okay. Over here, I have given an example of ResNet. So ResNet introduces two different types of blocks, the basic blocks and the bottleneck blocks. And the main feature, what they basically told is amazing to avoid overfitting or exploding and vanishing gradients is a residual connection. So we'll talk a little bit more on this, and hopefully everyone will be able to understand this what ResNet is. You guys can look into SE ResNets later on, and there's also models like ConvNext, DenseNet, and all that stuff. So you guys can try different models out. That's why you have study groups. Each person can try different models and do ablations with that. So in a traditional feed-forward neural network, data flows through each layer sequentially, right? I think that's what most of you guys have done for homework 1P2 as well. But what a residual connection does is provides us another path of the data to reach to the latter part of the neural network by skipping some layers. So what it means is basically, I have an input data, let's say X, okay? I save that, okay? And then I put the data inside through a model, okay? And ensure that the shape is still same with respect to my input. And then I add the input again and just go forward again. I repeat this process n times. That's basically just residual connection. It's so if anyone's a mechanical engineer over here, it's similar to how controls works. So yeah. But any doubts on residual connection? I know like it might go over your head right now, but once you guys actually do the lectures and you guys are able to come back to the homework to bootcamp, which we are recording, it will give you a small gist on how it works. So how do they help? Basically, residual connections help in mitigating your exploding gradients and vanishing gradients. And on the other hand, also the training process of the neural network with residual connection shows to converge much better than without it. This is true for most of the CNN cases. For linear layers, I think people have tried it. It hasn't worked very well, but at least for CNNs, it's pretty good. So without residual connections, the gradients usually get weaker, meaning like as you go along through like different layers, your actual signal gets very weak, and you don't want that weak signal to be your final output, right? So because of that, you add an extra boost, which is basically either your input or from middle connection or wherever you're getting it from. So that's what's basically just residual connection doing. So how do we perform residual connection? So first you have to do an identity mapping to X. Basically you take X, say Y is equal to X, and you just save that variable. Okay. Then you perform basically a feed forward. You go through different layers, and with one of the outputs where the shape matches your input, you just add it up. You just do basically, if X is your output, you just do X plus Y. That's pretty much it. Uh, and usually after that, you can apply an activation function. Most of the time it's ReLU, but I think since most of you guys must have done homework 1P2, you must have also found out that GELU performs really well, CELU performs really well. So you guys can try out different activation functions. But if you look into the original ResNet paper, they used ReLU. So maybe converting from ReLU to GELU might perform better, who knows? I might. So let's talk about the basic blocks. So basic block is just basically a normal convolutional that is happening. That can be based on whatever kernel size you're using, whatever input and output channel you want to use. Uh, it's nothing too fancy. It's just telling you that they're using 3x3 kernel size for your convolution, which is again going to be just one line of code, and you can basically make a function out of that and keep calling that thing out. And after basically doing your basic block, you just can apply a skip connection, which is residual connection. And after that, just apply a ReLU. That's pretty much basic block. Bottleneck block, on the other hand, is a little bit different. What it does is it takes your model, your input, it makes it go down and condenses the information into, let's say, a smaller channel or let's say a smaller shape of your output. Let's say embedding might be like 100 dimension, and then you again come back to the original space. So that kind of gives you an intuition that condensing it and then bringing it back to the original shape might give more information. And that's what basically the ResNet paper was able to prove with their different ResNet architecture. I think they introduced this with ResNet 50, if I'm not wrong, but yeah. And then you basically just use the same regular 3x3 convolution. You basically bring your channel to 64, and then you bring it back to the original shape. And then you apply the residual connection. So this is just a small intuition on how the code works. Again, you're not using linear layer. We don't want to give you the code for ResNet. We want you to identify, go through the paper, see how they are doing it, and then just come back and code it by yourself. So in the slides, I just put the same thing as how basic block works with a linear layer, but that's just to give you an intuition. And same thing for the bottleneck layer. So just have a look through it once you guys are doing your CNN lectures. And hopefully this will make sense intuitively why it works and how it works. But I'll not go too deep inside this uh, coding like of the linear layers and stuff. There are, I think, yeah, so there are one, two, three, I think there are like four different models. They have ResNet 18, 34, 50, and something with 100 as well. So they have different type of ResNet models. You guys can try out yourself, or you can also make your own custom ResNet models by changing up the number of channels, by changing up your kernel sizes, etc., etc., etc. There are different techniques you can employ. So for this homework particularly, we TS tested out with our own custom ResNet models. Trying out with the original one may or may not help, so you might need to do a thorough evaluation study on that as well. I hope I haven't lost anyone till now. If I did, you guys can calm down. We haven't come to the CNN lectures yet. So once you guys actually learn about CNNs, you'll be able to understand what I'm talking about. I know that I'm going a bit too quickly. That's because we have homework 2P also be taught, and I have to also go through like my friend over here has to go through the different loss functions as well. So for that, I'm going a little bit fast. Sorry about it. But don't worry. So just take 20 seconds to breathe and calm yourself out, and hopefully like everything works out. So I'll see Piazza till then. Oh, sorry, chat. I hope you guys are calmed down. So let's go back to the lecture. So how is a general architecture flow for this? CNN architectures are basically divided into different stages. And these stages define like how your model is going like through different forward layers. So usually you start off with stem, then stage, and then finally a FC layer or a classification layer. So stem is nothing but taking your original image and condensing it down to whatever image you want for your model to train. Stage is nothing but you using different type of blocks, which can be your basic blocks, bottleneck blocks, etc., and applying the residual connection onto it, and keep repeating that for like let's say n times or n plus one time or how many ever you want. And after you get an embedding from here, you apply a classification layer, and that classification layer will help you do your face classification task. But when you're doing a face verification task, you basically be removing your FC layer and you only be using your embeddings. Usually embeddings perform well compared to a classification layer, but there are times when I also saw that the classification layer will also help you perform well in verification. So you guys can try both the things out, but usually for face verification, you remove this bit, so the FC or classification layer, and you only use the embedding. And there are different losses also. So losses, how we'll be telling you about it. But yeah. So a small summary on the CNN part. There are three different ways of doing CNNs. One is a normal convolution, which is basically you telling the number of what kernel size you want, what is your in channel, what is your out channel. This basically mixes up your channels and your spatial locations, which is pixels. And there are other two things that is there, which is introduced by ResNet as well. One was pointwise convolution, where it sounds like some big high level thing. It's nothing. They just make the number of channels same. So your in channel is equal to your out channel. That's basically your pointwise convolution, and you make your kernel size is basically equal to 1 in that case, because you're just doing it with 1 pixel. Depth wise, on the other hand, it's basically you what do you say? So depth wise is just mixing up information on different spatial locations. That's basically you telling your kernel size is 3, and you're telling your in channel is X, and you basically do a convolution with that. So it's really, if you look through the paper, there'll be a lot of like these gibberish kind of words, but you can just put it through ChatGPT. It'll tell you essentially also what it is. So don't worry about doing it. It's whenever you find these kind of gibberish words, just try to identify what they actually mean. And it's actually very simple on what they actually mean. So yeah, let's come to training, monitoring, testing, and Kaggle submission. So over here, overfitting may not necessarily mean your train accuracy is going to be extremely high, your validation is going to be extremely low. You're going to be saying in this case that your model will be overfitting, and that's totally fine. There are times when your accuracy of training might be 100%, but your model might be still learning a lot. So even if your training is accuracy is 100%, don't think that okay, my validation accuracy won't improve much at that. You never know, it might actually improve. Homework 2P2 is a little bit different in that case. So over here, if you see, I have also written over here, there's a recent research that finds that some of the problems, like where training accuracy hits 100% in 10 epoch, but your validation accuracy might be less than 50%. But let's say on Y epoch, your validation might actually hit 100%. You never know. So just play around with your augmentation techniques, try see what best more accuracy you reach, and then just train it for like let's say 100 120 epochs and let your model train, and who knows, you might guys reach high cutoff. So of course we can't train for very long, but train until your validation stop improving. So that's the main area right now. So you do know that we have train split, validation split, and test split. Try to basically keep training your model until you see your validation not improving at all. Don't look into your train function a lot in this homework, I would say. And of course, you can use different LR schedulers. There is cosine annealing, there is radius LR and plateau. Warm-ups have a lot, so use warm-up as well for this homework. So how to tackle overfitting? There are different regularization techniques, especially for let's say CNNs. In this case, dropout usually don't help because what do you think a dropout would do with images? Any idea?
Facial information.
What happened?
Like drop this facial information.
Okay, that's the information. So what dropout would essentially do is if I had let's say 256 by 256 images, if dropout would essentially just randomly take pixels and blacken them out. You don't want it to basically take random pixels in 256 by 256 cross plane and just flash that out and be like, okay, now this is a new image generalize it to this. You don't want that to happen. So instead of that, you can use something called drop block, okay, which basically blacks out the block of pixels at one time. So that might perform better compared to a dropout, which just basically does it over different pixels. There is something called stochastic depth as well. You guys can have a look into it. Label smoothing, we have seen that it performs very well. And using label smoothing is very easy, straightforward. When you're defining your cross entropy loss, just do a comma, label smoothing is equal to 0.1, 0.2, whatever value you want to try it out. Yeah. So there are different bag of tricks for image classification tasks. We have put the paper over here, which you can have a look into and see what are different regularization techniques that might help you out. But yeah, feel free to use dropout after your final linear layer. I mean, like before your final linear layer, like at your embedding space. But yeah, you guys can focus on this also. Here we give you a little bit of different optimizer techniques and basic learning rates, which was used in ConvNext. So you guys can follow, if you're using ResNet, you can use a similar things what they used in the ResNet paper. If you're using SE ResNet, see what optimizers, hyperparameters they use for SE ResNet. That is a good starting block usually. So yeah. Different loss functions, I'll hand it over to her.
Okay, thanks, Hannah, for the detailed introduction on the Voodoo architecture you'll be using in this homework. And in the next, I'll cover several loss functions you will be using for the face verification tasks. Oh, sorry. So before delving into the detail of the loss function, let's first look into the face verification system. A face verification system basically takes a pair of images of two faces, and the system is expected to output 0 or 1, like whether these two faces are from the same person or not. So perhaps the simplest way to design a face verification system is to training a face classifier. as we did in homework 1P2. However, there's some limitation with the face classification. So to train a face classifier, usually we have a data set of different faces of different identity, and we label each identity with different IDs, and we train a classifier, basically a CNN classifier on top of these images to predict their identity IDs. So why can't we, a simple idea is just, why can't we just use this CNN classifier to do face verification? Any idea? So think about this case. Once you, let's say you have a 1,000 identity in your training set, and you train your face classifier on top of this 1,000 identities. And in face verification, we might encounter some identities that is not in your training data set, which means we might encounter an ID of like 1,001, 1,002, and your system won't be able to predict the new identities. And you have to do that, you have to retrain your face recognition system or retrain the entire classifier to include the more new identities. And we don't want that in practice actually, because we don't want a face recognition system to be retrained every time once there are more new identity to be added. So here are more formal reasons why classification cannot do verification well. Well, the first reason is the thing we just talked about. A classifier can only perform closed site recognition. Closed site here basically means the classes your classifier can recognize is basically the classes in your training data set. And once there are open set new identities every time, you need to retrain your classifier. Here, open set basically means once there are new classes or new categories or new faces in your classification system. And a shortcut, like a solution to the above question is actually we just use the backbone of the CNN classifier we just trained, and we extract features of different faces, and we compare these features to see whether the faces are of the same identity. And usually, if you have features, if you have a well-trained CNN classifier, it will compare the feature space will be able to do such comparison. But we'll see that the features learned by the classifier with especially cross-entropy loss is usually not very discriminative enough. So here is a feature visualization of our cross-entropy loss. On the left, I'm showing the features of 10 classes. You can imagine that that's 10 identities we trained on for 10 different person. And on the right, I'm showing the same 10 classes with the confidence of the classifier. Basically, confidence means the probability of the classifier predicting that this data point belonging to this identity. So you can see the reason why it's not a discriminating enough feature space is because F1 and F2 on the left figure are from different identity or different classes, and F2 and F3 are from the same classes. Yes, if you compare the distance between F1 and F2 and F2 and F3, F1 and F2 actually have smaller distance compared to F2 and F3. We don't want this if we are using a CNN classifier to do face verification. And if you do want to know why this happens, let's take a closer look at the cross entropy, especially the equation of cross entropy. On the left, I'm showing a illustration of how our CNN classifier works. You have an image X and you input into a feature extractor, usually a CNN, and you get some embeddings, let's terminate as Z. And you train a classifier, so basically usually a linear layer, and you can also use multiple linear layers to predict a logits on top of the face embedding you have from your feature extractor. And you train this logits with your labels in your training data set. And before you train, you usually train a classifier using the cross-entropy loss. And to compute the cross-entropy loss, you need to convert the logits from your linear layer into probabilities using a softmax activation. And you conduct some multiply with your one hot label with this probability. And if you do some rewriting with the cross-entropy loss function, you can just look into the last line actually, and ignoring the derivation process, which is kind of boring. And if you're looking into just the bottom line here, what cross-entropy loss really did is actually encouraging the logit score of your target class Y to be larger than the maximum of logit score of your other classes. This means during training, you're actually extracting the feature of your same classes to be larger than the other classes, which give us the feature space we just saw, because it's extracting, you want the logic score of your target class to be larger than the logic score of other classes. That's why the feature space is showing in a splitting shape. So what's our better feature space? Actually, I'm showing here, which is a much better feature space, because you can see the features of the same classes are clustered more together, and there is a clear margin between different classes. So what are better features? Formally speaking, a better feature basically means larger intra-class similarity and a smaller inter-class similarity. Or if you speaking in distance, it's smaller intra-class distance and the larger inter-class distance. And if you're speaking in human language, it basically means we want the features of the same classes to have larger similarity or smaller distance than other classes. So how to do that? We usually do that with different loss functions, or we can say that we use different loss functions to learn more discriminant features. So the real question here is basically how do we maximize the similarity between the positive pairs or minimize the similarity between the negative pairs? And we'll see how to do that in two paradigms. The first paradigm is usually known as metric learning or pairwise learning. And the second paradigm is basically usually known as margin-based softmax. And you will see these two paradigms in the write-up of Homework 2P2. So I'll briefly go through each of the paradigm. In metric learning or in pairwise learning, it's actually quite illustrative to the name. So basically in this paradigm, we want to directly apply some loss functions on the feature space to encourage the features of the same classes to be larger than the similarity of other classes. And in terms of loss function, we can see a simple loss function as here. So basically we want to minimize this loss function to maximize the logic score of the positive pairs and minimize the logic score of negative pairs. And we also want to encourage a margin between the positive score and negative score, which terms as M. Basically means we want the logic score of the positive pairs to be larger than the negative pair by a margin of M. And usually there are several loss functions to which you can use in Homework 2P2, like center loss, tributary loss, unpaired loss, and contractive loss, which we encourage you to explore different loss functions to achieve this. And another paradigm is basically terms as margin-based softmax. So in margin-based softmax, we can first look into the first equation, L1. L1 is basically a loss function of our normal constraint P, where you compute the softmax over your linear layer times your feature here is X. And in margin-based softmax, basically it means we want to encourage some margin in the logic score computed by the linear layer and your features. And how do we do that? So usually we normalize the weight vector W and the feature vector X to have a unit magnitude. So the dot product between them is just the cosine angle between these two vectors. And you encourage some angular margin, as we saw in tributary loss, to encourage the positive score to be larger than the negative score by a margin of M. And there are also several different loss functions to achieve this, such as AM softmax, sphere phase, cosine phase, and arc phase. And usually there is also combined margin phase. So basically they're all designing different margins and how the margin should be added into the softmax function. So that's basically the loss functions you are going to try with this homework. And you're allowed to use, as shown in your notebook, you're allowed to use the PyTorch metric learning library to directly use the loss function instead of implement by yourself. But actually, utilizing the loss functions from that repo, from that library requires some understanding about the loss functions. So I still encourage you to read the original papers about different loss functions to understand them and to understand how you do to use the loss functions directly from the library. So here is some tips how to get started with Homework 2P2. The first step will be using a simple network and the cost to be lost for your early deadline to achieve some initial score. And then you should try some better architectures like ResNet or ComNext with the cost to be lost to see it's performing better than the simple network. And then you should add more data augmentation as Hanan introduced and try to reduce the overfitting of your network. And the next step will be training the loss function we just introduced, either the metric learning loss functions or the margin-based loss functions. And usually you can achieve very high score by fine-tuning your cross entropy trained models with other loss functions. And there's several tips you can get this homework started. And I think that'll be all. Any questions regarding the loss functions or the architectures or the homework in general?
Is there any limit on the number of parameters like these?
Sorry?
Is there a limit of parameters?
No, there's no limit on the parameter for this homework.
Said 83 parameters.
Oh yeah, just ignore that. We changed the.
In fact, you won't be using a limiting parameter for this homework.
We'll probably.
It's
be-
actually too large. Usually, I think the suggested size will be like 20 milli, around 10 milli, 20 milli. Yeah. Which slide?
On this instruction, we need to focus on the function, we don't need
We do encourage you to explore different architectures, but in fact, you can achieve very high score with just those functions in the like ResNet or a random architecture.
I had a question. Can you just elaborate on the last point, which says finding out probability loss with other laws?
Sorry, can you repeat your question?
Slide.
Mm-hmm.
Can you just elaborate? The next slide, sorry.
This one?
The slide with the 5 pointers that you just showed.
Okay.
Yeah. The last point, can you elaborate on that? Like,
Oh, yeah. So basically, usually you can, it's kind of similar to the pre-training and then fine-tuning paradigm. So basically, you first pre-train your network using a cross entropy loss and with some heavy data augmentation and heavy regularization methods. And after you pre-train your network using the cross entropy loss, you can take the network width, replace the head, and fine-tuning it with some other loss functions like the arc phase or trivial loss. And you will achieve better performance than just using cross entropy. Or it's kind of similar to the pre-training and then fine-tuning paradigm.
Any other doubts, anyone? So, we'll move on to homework 2P1 in bootcamp, and after that, we'll get into the pizzas. Special counts. So. I know many people will be a little bit lost in this homework to bootcamp. It's totally fine for now. Once you guys go through the lectures and you actually come back and refer to the homework to bootcamp video, you should be okay. So don't worry too much about it right now. We are just giving a little bit of a small taste of it, and hopefully everything will be fine. Cool. I'll just share it.
Oh, so that you can see the spectrum.
Still recording. Yeah, cool. So, any doubts in Canada? Cool. All right, here you go.
Should we start or wait? No, we wanna wait. We wanna wait. Can wait 5 minutes. A lot of people have went to the washroom. Let's wait for. Wait for 5 minutes. Okay, we'll just wait for 5 minutes for everybody to come back. If you want to take a break, you guys can do that. Oh, we should.
No, this is the right thing. This is change it. Change it. Stop sharing. Yeah. I changed. I have a nice idea. Then.
Also, for the loss functions, everybody's looking that should look into something for the type. So I don't try to follow up the.
No, I mean.
So like. Those have most of the directions.
Yeah, I think this. Okay, we can start, right? Should we start? I think people are not. Away. Or. People are like finish it up.
Yeah, yes. Also the institution of organization. I would exceed it. Yes, and what is it? Actually, here, give me like. Yeah. So that. And I use rate. Like, yeah, data. Everything has to be. Yeah. Let's drop. Zero point. In certain cases, final layer gets okay.
Okay, let's start with homework 2 part 1.
So when you do that, so you don't want to use that strategy. You have to. So that is the information that I'm going
Okay, so as we all know that homework 2 is all about CNN and the lectures haven't started on CNN. So I'll just give you a brief overview about it. So CNN has all these layers. The first one is the convolutional layer where we use filters, where each filter goes through the image pixel at a time and extract features. Then there is a pooling layer which extract the information from those features. And then we flatten that layer, pass it to MLP, and then classify the output. So basically, um, in CNN, in CNN layer, we will be doing resampling, which includes upsampling and downsampling. So upsampling is basically you just bloat up or fill up your input size to make it bigger. And conversely, downsampling is you reduce the size of your input, but preserving the information inside it. So we will talk a little more in depth about the resampling part. So in resampling, we use this to make convolution with stride not equal to one more intuitive. So I think a lot of you might not know what stride is. So stride basically is when a filter goes through an image pixel at it. So it goes through each pixel at a time. So stride equal to one means the kernel goes one pixel at a time. But in stride not greater than one, it jumps multiple pixels at a time. So resampling helps you make it more intuitive for this stride part. And so in this part of the homework, we recommend you not to use for loops, but use like NumPy library because NumPy library is good for array that uses like low level optimization and parallel processing. So you can use the np.cron library. So this library, it finds out like the Kronecker product of two matrices that are in consideration. So the output of np.cron is also a matrix. So first element of matrix A is multiplied by all the elements of matrix B. And you can look up the documentation for more detail. Similarly, you can use array slicing, which is pretty easy. Like you just specify your start, end, and the number of steps you want to take to uh, resample. So there are a few points that we need to consider. First is that consider the shape of the matrix when doing upsampling or downsampling, and save your shape in forward method because the gradient should be same for the forward and the backward function of the input. Okay. Next, we will talk about convolutions. So convolution is just like the how a filter goes through the image, and there are two ways to do that. First one is using for loop, which is the worst way to do it because as like you will be doing conv 2D and there you will be using like four for loops, three for loops, and that will take a lot of your time. So for loops are really bad, and that's why we recommend you to use tensor. So it is very fast. It consider issues like broadcasting or matrix multiplication. And you can check out the appendix. We have given you how to do tensor. But we can go, we'll be going into more details about how to use tensor in your homework P1. So, so it simplifies the convolution by reducing the number of for loops, as I said. So tensor dot is simple dot product, which is element-wise multiplication and then addition. So a thing to note is that it doesn't perform the whole convolution, but just reduces the number of for loops for you. So when we have our filter go through an image, we do a dot product of filter with that pixel, that portion of that image, and tensor dot instead of using many nested for loops, it does exactly that, but just reduces that the number of for loops. So we in this homework we have con 1D and con 2D. So in con 1D you'll use, I guess, one for loop with tensor dot, and with conf 2D you'll be using two for loops with tensor dot, and you'll pass your you'll pass function. So let's look at this example. Uh, so here the input matrix X, which has a dimension of ABC, and the weight matrix W has a dimension of PQR. So in tensor dot, we look at the dimensions along which the shape matches. So here we are assuming that B is equals to C and C equals to R, and so the output matrix would have a shape of A cross B. So in TensorRT, you have to, it is important that you match at least one dimension, because note that convolution happens, like filter goes through an image only one specific section at a time. And so it is important to, match the dimensions. So another tip is just print out your shape, and then you can match it with your test shape, and that will help you out how to use your tensor dots as well. So, in this example, uh, the dimension of input is AXCY, and the output and the weight matrix is XPQY. And these two matrices we need to see in which dimension the shapes are matching. So, in the first matrix, the shape X, the dimension X is in the second position, and the second matrix has it in the 0th position. So note, tensor dot doesn't require that the dimension that matches have to be in the same location, and they can be at any location, but you need to specify that in your tensor dot function. And Right, yeah. So I think, yeah, that's it about tensor dot. Uh, we can move on to conv 1D and conv 2D. So basically conv 1D uses like is a one dimensional, and 2D is a two dimensional. And when we transition from when you transition from in your homework from 1D to 2D, you have to take care of that extra dimension, and as well as you have to take care of something extra which you'll find in the write-up. Um, Plus, I'll also mention that write-up is really great. It has graphical representation of almost everything, convolution, how you perform pooling. So when you get an intuitive idea through it, when you get an intuitive idea, it'll help you like to understand the logic and perform all the functions. And pooling, since we haven't covered it in the lecture, pooling is just extracting the feature, and you use like mean pooling or max pooling. So basically, max pooling is extracting the maximum number from that pool. And you'll learn why we use pooling more in the lecture slides. So in pooling, you can use np.max or np.unravel index to reduce the number of loops, or you can use like multiple loops in pooling as well. Um, Back propagation in pooling is a little harder than forward propagation, but if you understand the logic, like I said, it'll be like a piece of cake. And look at the write-up for more images and more explanation. And I'll pass it on to Yichin for the next section.
Yeah, the next session is about scanning MLP. You're gonna learn about the details of it next week during the lectures, but I can just show you some like big picture of what is scanning MLP. So scanning MLP in one sentence, it is to mimic the performance of the convolutional layer using the MLP. So let's first talk about what is the key difference between conv1D and the linear layer. So do you guys remember that in homework 1 part 2, for the data processing part, in the last part of it, you have to flatten the data set into the 1D, like very long, very long stuff like that. Something on the right-hand side of the slide. So this is what you put to the linear layer. But for the convolutional layer, you don't have to flatten it, you just put this whole block into it. So yeah, this was just basically what you did in homework 1 part 2. For each of the block, you have to flatten it first and then put it to the MLP, and then you get the output of it. So when we want to transfer the linear layer to Comp1D layer, I'm gonna tell you like what are the parameters, what are the hyperparameters you need to put to into the parenthesis of the Comp1D. So in channel basically means like how many features in the input layer. So we can see that there are 3 rows in the input layer. So the in channel size is 3. And the out channel is how many features you want for your output. So in out channel here is 2. And kernel size means how many points you are interested in one time. So you see that there are like 3 lines, 3 lines here, and the kernel size is 3 here. And the last stuff is about the stride. Stride means that like how much step we want to move for each time. So you can see that like for each step it moves only 1 step to it. And in the end you can get the output like that. Yeah, thank you very much. This is all for the bootcamp of homework 2 part 1. Do you guys have any questions? No? Okay. Let's just